Assalamu alaikum. My name is Syed Sanjam and I'm one of the authors who contributed to this research. The title of this study is Image to Image Attire Transfer for Virtual Trial Room. As the title implies, our work is concerned with image to image translation. What we're trying to do here is to seamlessly transfer the outfit of a person to another person of arbitrary shape and size. For the rest of this video, I will try to answer some of the whys and hows of this study, and hopefully after the end of this presentation, you will have a clear perception of our work. It goes without saying that this study is focused particularly on the fashion domain. Before we even start, I feel the need to justify why we chose what we chose. Fashion plays a big role in our everyday life. It matters to the economy, to society, and to each of us personally. Millions of dollars are being spent on the fashion industry each year, and we truly believe this area is so full of interesting components and there is so much room for exploration. The idea of image-to-image translation first came to our mind after exposing ourselves to generative models. To be a little bit more specific, we are talking about generative adversarial networks, or simply known as GANs. A variation of GAN, which is cycle GAN, is widely used for image-to-image translation, and we became quite fascinated by it. The cycle GAN is an extension of the GAN architecture that involves the simultaneous training of two generator models and two discriminator models. One generator takes images from the first domain as input and outputs images for the second domain, and the other generator takes images from the second domain as input and generates images for the first domain. Clearly, there is a cyclic pattern to notice here. The discriminator models are then used to determine how plausible the generated images are and update the generator models accordingly. A very famous example, which is horse to zebra translation, can be seen on the screen. Another popular example for image to image translation is this one. These instances clearly indicates that there are a number of sectors where cycle GAN can be very useful. Another computer vision technique we came to know about is face swap. We wanted to do the same thing, but instead of human faces, our target was to swap clothes. Right now, we can see a demonstration of the face swap method. We will talk more about cycle GAN and face swap in a minute, but now let's take a look at some of the fields where these computer vision algorithms are largely being employed. So our point is, if done correctly, a computer vision approach for attire transfer can be groundbreaking. Now that we have established where we are coming from, I will try to talk more about our goals, approaches, and of course the result of our study. As we stated earlier, it all started with cycle GAN. We already know that image-to-image translation is possible using cycle GAN, but we asked ourselves, can it also achieve what we are trying to do? So we applied cycle GAN to the lookbook dataset, which contains thousands of images. But the output, as you can see, was not satisfactory at all. The reason being, cycle GAN works with paired dataset, like the ones we have seen earlier, horse to zebra or apple to oranges. While the cycle GAN approach was mostly experimental, we relied heavily on the face swap algorithm. But apparently, this algorithm works on certain constraints. For this algorithm to work properly, we need landmark points. While facial geometry is somewhat fixed, we cannot say the same about human clothes. So again, it was not possible for us to continue with this approach either. Another well-known approach for a similar task is known as pixel DT GAN. We tried tweaking the parameters of the model, but random inputs do not produce acceptable results. These photos here are produced by the Pixel DT GAN model. From the outputs, we can conclude that while Pixel DT GAN can extract the outfit to some extent, it cannot do what we are trying to accomplish. Finally, we learned about the liquid warping GAN, which is a similar work in the same domain. It has a couple of modules, one of which is involved in the appearance transfer. This framework works on the impersonator dataset. It produces much better results comparing to the other GAN-based approaches. However, in the outputs we have produced, the human body shape is completely distorted in most of them. What it means is, this model can transfer the attire but does not preserve the original shape. We wanted to do better. At this point, we knew we had to introduce something new or combine a couple of existing techniques to do what we are trying to do. So we divided the problem into sub-problems, the first being identifying the clothes and the second one is transferring it. To extract the clothing items, we need to dive deeper into the world of image segmentation. There are two types of image segmentation, semantic and instance. Both of them are pixel level classification. But while semantic segmentation does not classify each pixel of the class separately, instance segmentation does it. Since we are trying to localize only the clothing parts, we came to realize we have to work more with semantic segmentation. And with segmentation, it was also necessary for us to focus only on the foreground and ignore the background as much as possible to avoid getting noisy result. This is where the grab cut algorithm comes into play. It is used to create separation among background and foreground. As you can see on the screen here, this algorithm is able to extract the foreground from the background. To put segmentation into play, we have taken advantage of the UNet architecture. It is a deep convolutional network often used in the task of semantic segmentation. We have created a small dataset of our own to train the UNet model. The dataset contains images of three types: original, body, and race. We feed the model, which receives as input a raw image and outputs a three-dimensional mask. Here, it is able to recreate from the original images the desired separation among skin, background, and race. In this way, when a new raw image comes in, we can separate it in three different parts: background, skin, and race. And therefore, we have solved our first sub-problem, which was to be able to identify the portion of the outfit in an image. If we look at some of the outputs, the result seems pretty convincing. However, we wanted to integrate UNet to a generative approach to see how it all works out. And to our surprise, it does better than we anticipated. This is a summarization of all our approaches, and from the data presented in the table, it is quite clear that we had to consider liquid warping GAN one of our key components. Before we move on to our proposed methodology, we feel obligated to clarify the difference between the following terms: target and source. Target image is the image of the person whose clothes are being moved, whereas source image is the image of the person on whom the clothes will be moved. Now that we know the difference between the target image and the source image, let's talk about our proposed method. First, we feed both the target and the source to our liquid warping GAN framework and receive an initial output. From what I have said earlier, we know that it is very likely that the output of the liquid warping GAN framework is distorted and the shape is not preserved. If we take a look at the output generated by the liquid warping GAN, we can clearly see that the shape is simply not right. We need to process this output even further to produce a better result. After that, we create masks for both source image and the liquid warping GAN output using UNet and GrabCut. In other words, we now have a clear perception of the region where the outfits are in both images. The reason we are doing this is because we want to explicitly define which parts of the images we want to focus on. Since we are working on outfits, this is the only part in the entire image we are interested in. We can visualize this process clearly from the image on the screen. Finally, we combine the two masks to avoid selecting unnecessary pixels, and it can be seen that the pixels other than the clothing region of the images are ignored, resulting in a much better output. We have also included a detailed diagram of the complete process for better understanding. If we take a look at some of the output images we have produced, we can see that this method is very likely to preserve the shape and less likely to produce distorted images. Now it's time to compare our results with the ones generated using liquid warping GAN. Let's take a look at this particular example. We can say with confidence that the output we have produced is clearly less distorted and more realistic. But the question remains, is this method perfect? The answer is no, it is not. There are certain drawbacks that we could not overcome during the period of this research. Our UNet, which was used entirely for segmentation purpose, was trained on very few samples. As a result, there were times the dress segmentation was not accurate enough to produce the best outcome. Here's an example of such scenario. The shirt here is full-sleeved, but our model could not segment the entire garment. Therefore, there is no way we can perform a proper attire transfer if the segmentation is not done properly. Theoretically, this drawback can be eluded if the UNet model is trained on a large enough dataset. Our approach is not perfect, but we strongly believe it opens a door for an entire world of possibilities. Our attempt also indicates that it is only a matter of time for AI and computer vision to become an integral part of our everyday life. In the end, we can all agree that this study has been a salutary experience for all of us involved, and there is still so much we want to discover. Thank you for your patience. We all appreciate this tremendous opportunity to present our work on such a huge platform. It is a privilege to be a part of the scientific community. Thank you again. We will greatly appreciate any feedback. Have a nice day.